Hello, and welcome to today's webinar. Produce more precise, distortion-free, and repeatable microbore medical tubing. My name is Jim Colari. I'm the editorial director of Plastics Technology magazine, and I will be your moderator. We have two presenters this afternoon, so please let me introduce you to both. Bob Bessemer has worked for several downstream plastics extrusion equipment manufacturers over the past 36 years, both with engineering development and sales, and now he is the Vice President of Extrusion Technology at Novatec, Inc. With a major focus on developing, sizing, and cutting equipment specific to medical and pharma applications, Bob has 6 patents. A major goal of his has been to better control the variables of the extrusion process and eliminate the so-called black art. Bob's co-presenter is Larry Alpert. Larry is a longtime medical tubing executive who now runs his own extrusion consulting company, Med1 Extrusion. Please feel free to ask questions at any point during the presentation. Simply detach the questions pane from the panel on the right-hand side of your screen and type in your question. We will get to answer as many questions as possible following the presentation. I'd now like to turn the program over to Bob Bessemer and Larry Alpert.
Hello, this is Bob Bessemer
and Larry Alpert.
And today we're going to be presenting a webinar through Novatec, and we're going to talk about producing more precise, distortion-free, and repeatable microbore medical tubing. And again, I'm Bob Bessemer from Novatec. You can read the rest of this. I've had a lot of years in producing downstream equipment, over 35 years. For multiple different companies and done a lot of experimenting, but my biggest thing in life is trying to remove the black art from extrusion and make it the science that it truly is.
And I'm Larry Alpert. I'm a veteran of the industry of over 35 years in focusing on medical device applications. And I'm one of the guys that has pushed Bob over the years to make the equipment that we need to be able to move forward.
And with that, we'll get started.
So we're talking about understanding the hot gap, which we define as the gap between the hot die face and the initial contact with the cooling process, and how it can actually have an effect on the actual part that you're making and its properties.
And with that, today, we are going to be going through multiple slides, and want to let everybody know that as a person that registered for this webinar, you will be able to get a link that you'll be able to see for up to a year, so you'll be able to replay this webinar at any time. And today we're hoping on this section with understanding hot gap that you're going to be learning the definition of hot gap and how it impacts your process, how material properties can be affected by the hot gap, and how tubing sizing and stability can be affected by the hot gap, and why the hot gap we feel is critical validation point and a new and unique method of adjusting the tank with improved precision.
So as you see here, this is kind of a typical depiction of a hot gap, which is basically the area in between the die face and the cooling medium. It's pretty straightforward.
So as we're showing here, and we're going to go into obviously a lot more detail on this, but Larry is going to be talking about the die and its importance. And again, there'll be a specific slide. We'll be talking about this distance, the die swell, and the difference in heat transfer in air versus when you're in the water.
Can die sizing or land length affect hot gap spacing?
So Larry, when the die land length is longer versus very short, how does that affect the spacing that you might have when we're looking at this gap?
Well, the land length will determine the amount of swell that the polymer sees, the memory effect of the polymer as it comes out of the die. So normally there's an acronym that's used called land gap ratio that you would use in your calculations to be able to determine how much land that you actually need to ensure that all the other work that you did on sizing your tooling will actually work.
And again, we all know that that distance from coming out of the hot die gap, we've seen people be very close or be further away, depending on the drawdown, depending on the temperature of the plastic, depending on the material itself.
Well, yes, your die size will determine your basically what we used to call an angle of attack.
So again, this is one of those things, as I mentioned before, in making this process more of a science. That's why understanding your material, the temperatures, every part of the die, and thus the relationship of the face of this die to where that tube first enters the water is a critical point.
It will set up how the properties of your tubing.
So with that, Larry, just why don't we really quickly go through some material considerations and whether we're free extruding, non-contact versus contact sizing as far as the distance, what we call this hot gap.
Well, your distance is going to be predicated on some of the normal calculations that you see for tooling. So your area draw ratio, your direct draw ratio, as well as your draw ratio balance will dictate what your natural tank position is. So depending on how you want to set up your process, in a free extrusion, if you want to ensure limiting or slowing down the cooling, you may want to move your tank out further, as well as change your water temperature. Non-contact vacuum sizing is similar in that respect. And contact vacuum sizing, a lot of times, depending on the application, most of the time, you want your balance to be pretty well straightforward so that you're not using any internal air support. And once again, whatever that balance is will dictate how far out your tank is from your extruder.
And one thing that we know from years of experience, had this issue, people moving from free extrusion and then going to non-contact or even contact, especially, that the tooling will change. The die, the pin and the bushing will be a different size that if you try to use the same tooling you use for free extrusion and you go to use a contact calibrator sleeve or plates, that tooling, that drawdown ratio is going to be different. And not only that, but this hot gap is going to be different. In many cases, in calibration, where you're actually making contact between the tube and the tool, this distance, the hot gap is very short. Sometimes the face of the die is all but touching the front of the calibrator.
It can be, certainly.
So when we're going to go through, Larry's going to go and specifically talk about the material properties and how this hot gap can affect the elongation, the modulus, the burst strength, whether you want a crystalline versus amorphous, and even affect the tube surface finish, whether it's smooth or matted.
Well, in general, the cooling rate is going to determine how much elongation and the tensile values and the modulus, Young's modulus of the part. So you want to be consistent. You may not even have a specification for it, but you want to be consistent based on consistent with what you do and what you produce, so that when it goes to downstream processing, they don't have anything unexpected happening.
So basically the elongation is you're pulling it from the die and you're drawing it down, and the more you draw it down, the better your elongation gets.
Well, the more you draw it down, you can lower your elongation.
Okay.
You're aligning the molecules in the extrusion direction.
Just like they would with fishing line. They want a lot of strength in the pull direction. Whereas burst strength,
you would actually reduce that effect not to orient the polymer chains in the extrusion direction as much, so that you get more force applied from the inside.
So in a burst strength, you might want to have very little drawdown and possibly be very close to the die, where in elongation, you might be further away. That hot gap is going to be longer.
Maybe. It depends on the application.
Yep. And then in modulus?
Well, yeah, the area of deformation and the modulus of the tube will move along with the properties. Most people will discuss ultimate, but modulus is not an ultimate value. And so it takes into account the yield portion of the tube and curve underneath it. So it could certainly, it will certainly affect those, that value.
Very good. And something that I know is a lot of interest, especially in some of the materials, some of the nylon, some of the peaks. If you could just briefly explain, you know, amorphous, especially in medical tubing versus somebody wanting the semi-crystalline.
Well, all the pretty much all the polymers are semi-crystalline, and usually if you wanted to maximize either chemical compatibility or ultimate strengths, you would want to maximize your crystallinity. And to do that, you slow down the cooling rate. So normally you would have your tank out a little bit further. You might heat the water. Depending on the application, the water might have to be over the glass transition temperature of the material by a certain amount. And you want to cool it evenly as well.
Right. So when somebody is looking for an amorphous, they might have the coming out of the hot die, the gap very short and run into the water very, very quickly. So they're not really cooling through the entire wall at the same speed. So they're almost shocking it.
Right. There are a lot of components that are made that you, with downstream processing, that will build in the crystallinity needed. But you need the amorphous state, more amorphous state to be able to process them.
And again, semi-crystalline, and one of the materials that really comes to mind is PEEK, and we do have a quick video on the next slide that we'll be showing, but it's good to remember that air is 10 to 100 times slower at heat transfer as compared to the medium of water. So, but one of the difficulties always comes when we get such a big air gap. That distance is the problem, is supporting that part, and that's
and controlling.
Yes. So with that, we'll watch a slide, and Larry, if you could just walk us through.
This is a PEEK extrusion that is air cooled, and PEEK, luckily, is one of those materials that you can see when the crystallinity occur, where it goes from an amber to a gray coloration. So this is kind of a normal setup for PEEK. It does make it a little bit more difficult to control when you do this.
But look at, you can see that
you can see the frosting,
and then see it changes over to the crystalline state.
Yes.
Beautiful. And this is more of kind of a very typical, it might be also PEEK, it might be a relatively thin wall, because this gap might only be 10 to 12 inches. And in this case, they've actually put a small air ring to blow some air on it, some rollers to use for support. But again, the measurement between the hot die face and the point at which in this case is going into a calibrator, this gap should be a repeatable position and recorded.
Absolutely, because the amount of along with the line speed, the amount of time it takes to get to that point, you still need to be in the proper state for the contact vacuum calibration to actually work.
And Larry, if you could quickly discuss this gap also, as well as some other things, can affect the surface finish.
Well, some polymers, high density polyethylene is one of them, where it likes to actually see some air cool before it comes into contact. I've actually had some contact applications with high density polyethylene for dilators where your tank could be out 10, 12 inches. Other materials prefer it to be in more closer to minimize the air gap, so you're more of a molten state as you capture it.
But obviously, we're concerned today with this air gap in making a measurement because we want to keep a process consistent and record all these variables. But we know that this is a very important variable. But along with this, you mentioned to me yesterday, we were talking about the melt temperature can affect this.
Absolutely.
So,
viscosity, melt temperature.
So again, the idea of this is to be recording as many of the potential process variables as possible. So not just this air gap, but in this case, again, the melt temperature, the screw RPMs, everything should be recorded. And Larry, we've talked, and you and I have been dealing together for at least 35 years. And the normal method for moving a tank back and forth, we've talked about how critical, this gap is in making medical tubing. Actually, how close do we need to get back if we're trying to record every variable and we want to record and possibly validate what that hot gap distance would be? What would be a typical variation, or how much would you put? Would you allow 10 thousandths, 20 thousandths? What is?
Well, right now, I mean, unless you use a positive stop mechanism somewhere, somehow, some way, it's almost impossible to measure with any degree of certainty.
And we put this slide in because we're showing what the typical methods of moving a tank back and forth. For years, they've been a simple actuator, like a Thompson actuator in this case, or it could be a rack and pinion of some sorts. In this case, you have 5 turns per inch. In this case, you might have 1 turn per inch or less, but it's not a very, very precise method. And you and I have seen in medical applications, I have seen people put a simple bolt. They adjust the bolt out that they've pre-measured. So when they go, so they purposely have the bolt sticking from the front of their tank. And as soon as they bring the bolt, actually hits the face of their die.
Right.
And it's a relatively crude method.
Well, it is. I mean, the systems themselves have enough hysteresis in them that where your positive stop doesn't really work.
Right. So for this, we just felt extremely important. So we're going to quickly show you, and the next slide is where we think the industry is going to start heading, because we feel very seriously that this just is not accurate enough. A lot of times these handles are wobbling, and you can turn a quarter of a turn or then go the other direction, and there's no tank movement. It's just not precise enough. So for that reason, we've experimented and actually put on a servo actuator, and because we wanted to be able to pre-program repeatable where the tank is in reference to zero the die. So we know from the face of the tool how far it is and where exactly is the face of the die, and where we want that hot gap position to be, and be able to program that, and where we want, say, a string up or a startup position and a home retract position. And we did actually add a fast retract, and we'll talk about that. So if all of a sudden there was a jam up, we want you to be able to hit a button that's located in a good position so it can quickly go back to a string up position. We don't want people just shoving the tank out of the way. We're doing a precision process here. With that said, we'll go to the next slide.
5,000s, or even 10,000s at a time. So we've removed this feature because we just felt it was absolutely inadequate. And with that, we replaced it with a servo actuator. So Larry's going to demonstrate how we now move this tank with a servo actuator and not a hand crank.
Sure thing, Bob. Well, I mean, right now, the position that it's in now is for stringing up. And we have a preset hot die gap. So once you actually string the product up, it's basically touch of a button, and it moves into your preset die gap. You have these 3 speeds, three increments here. If you want to move your tank in, say 50 thousandths, press a button. You want to move it back 10 thousandths, press a button. These are all selectable.
So each of these numbers, these buttons can.
And with that, it's just showing you can actually see, because in a lot of cases, this gap is going to be very short. In this case, we just put a bolt on the end with a hole, and we're actually using vacuum to hold the water within the tank so we don't have water pouring out. But you are able to attain a position and go back repeatedly within 1 to 2 thousandths every time. And as we mentioned, we do have a fast retract. In a lot of cases, you might have an iris on the front, processing a small microbore tube. And if you were to all of a sudden start to puddle, in the old days, somebody might grab the tank, Larry, and just shove it back out of the way because you're ruining a $90 iris. So we didn't want to have to disengage the servo, so we put a button both up on the touchscreen and on the end of the tank. So if you're down at the puller, you hit this button, and it will quickly, at a faster speed, retract this tank away to our string-up position, trying to prevent people from just shoving the tank or bumping it out of the way, and then your alignment's out. It's just a mess. So with that, we will move on to the next subject. Today we do have two subjects we're going to talk about. So we split this webinar into two. And again, we will be available for answers and questions for both these subjects after this presentation. So we'll be very glad to take on questions talking about the hot gap and things that can affect that. And our next subject we're going to talk about today is the importance of the polar belt gap. And Larry?
Well, so in general, you know, we spend a lot of money and a lot of time in putting in a lot of controls on the puller itself, yet no one has really addressed the actual belt gap and ensuring that you have consistent contact and speed, as well as a pinch point for your product.
And Larry, like we've talked, we know that everybody has gone to servos, especially making microbore medical tubing, and everybody's gone to servo-rated reducers with lower backlash. So a lot has been done to get the speed of the puller, because we know the speed of the puller is critical to the process. We're pulling that hot molten plastic from the die through a cooling medium, whether it be air or a combination of water, and we're pulling it. We need to pull it at a very constant speed, because today we're holding tolerances not just of thousands but tenths on the walls, on the ODs. So the speed is critical. But as we mentioned, the thing that people have ignored to a point, and we're going to be covering that in great detail here today, is other than the speed, what can we do to the puller to ensure that we're making good contact between the belt and the extrudate in a way that we are getting consistent slippage and we are having consistent, if not having any, distortion. Again, trying to eliminate another variable. And these are small variables, but they all add up.
Yes, they do. It's basically using technology to be able to fix a mechanical problem.
So with that said, today we're hoping you'll learn is how the belt gap settings can mean the difference in processing a round versus a partially distorted tube, how belt gap can affect slippage between the belts and tube, causing variable pulling speed. So we'll spend quite a bit of time on that. And then how the different belt materials can affect slippage and potential for bowing, twisting of the tube, and particulate generation, and why belt gap we feel should become a validation point. And we'll show you something, a way that hopefully in the future will help to correct this variable. And with that, we're going to talk about the variable slippage and the pulling of the tube at varying speeds and variable tubes distortion, and we'll go into the details with these next few slides. With that, Larry, you want to talk about and this is, we're talking the operator looking at the front of the belt versus the back of the belt.
Yes, so, you know, mechanically, you know, trying to keep belts parallel, especially as a unit ages through its life cycle, becomes more and more difficult. I've seen a lot of belt pullers with the standard setup where you can visually see the difference in the gap from one end to the other.
Right.
So that creates a lot of problems in the process.
So we put this slide to show what would hope to be a perfect, and we're looking from the front of the belt to the rear of the belt, not the length, but from the front to the rear. And we want this to be within the thousands if it could be. And Larry, you've seen this on pullers, and again, we're going to discuss this more. If this belt gap is different, even by a few thousands, in this case, we're showing 5,000 difference, it causes this tube to actually bow going through.
It causes it to bow going through, and what happens is you end up having to tighten it up too much on a short distance, and you also push it into the radius of the roller.
Yeah. So you can have twisting, we can have bowing. And I've seen this on cutting applications also, where if the part actually will appear to be moving side to side and cause jamming once in a while.
Oh, yes.
So our goal is to find ways to help and use the type of belts we're going to talk about and the method of tensioning to try and get this gap straight, and also to have the belt contact over the length be straight, not have it touch at the exit end and be wide open at this end. So we're looking at it being parallel in both axes. It's very, very critical. And with that, Larry, I know you've seen this. Poly V belts have been used for years and years, and
Yes.
the wider the belt, the Poly V belt, the teeth don't perfectly match the sheave. And this has been a generator of particulate, because the belt will actually grind its way in. You get these little
Yes.
black specks. But in all these pullers, there are adjustment bolts on both sides. So you're tensioning the tensioner, and people will need to tension this side versus this side and look through the belt from the downstream end and make sure that they are parallel front to back.
Yes, they have to, or else you're going to get a twist in your tube. And a lot of people may not even notice that, especially if they're running a single lumen tube. Multi-lumen, you should be able to tell. But if you're running a single lumen tube, you could have a twisting motion in that tube, and you're going to change the physical properties of the tube when you do that.
Correct. And I've actually seen people request before they wanted a de-twisting feature on their puller, and this is what they actually consider the de-twisting feature.
Yes.
Is these two bolts.
Yeah, you just basically adjust it the wrong way.
So the Poly V belts especially, it's a thicker belt, and you do have to worry about this. So tensioning is very, very critical. We will be talking in a future slide even about the idlers, as far as the position of the idlers in reference to this level, where we may be talking about raising these idlers so we don't have to tension as much, because we don't want the belt hanging down in the middle and people having to over tension, causing
Yes.
bearings to start creaking. So again, we will specifically talk about that again also. One of the other issues, Larry, is for years and years, as long as I can remember, most pullers have used a round boom shafts with bushings, and they've typically had to have at least 2 to 5 thousandths of clearance, which can actually cause some rocking. So you could actually rock this up and down. When we're talking of making a tube that might be 10, 20, 30 thousandths, if this boom is able to rock a little bit, it could be leaning down a little bit. And again, we're talking thousands, and that's a critical thing. So from these bushings, we've gone to
Place them with precision linear
a
slide.
linear
bearings,
slide.
because we wanted these to be parallel in both directions within about a thousandths. Because we're making tubes that could have a wall thickness of a thousandths or less. So we've done everything we could to ensure perfect parallelism in both directions.
And again, so actually, I personally have used linear slides as much as 30 years ago, and just recently with Novatec come back to linear slides, because again, we're not trying to produce a product just like everybody else is. We're trying to help our processors make a better tube and be more consistent and be more precise. So these linear bearings.
Well, one of the problems that you have with the older style design is somebody could be having a problem with it and not even know it and never be able to solve it.
Right. Well, if those booms are sloppy and the things are kind of hanging on a little bit of an angle, they could be trying to tension their belts, not realizing that they've got this rocking condition. And this is a good slide, and we'll show another one that you can actually see that these idlers, in this case it's the 6-inch puller, these 3 center idlers are actually raised a hair higher than the 2 end rollers. And this is done so you don't have that hanging effect, especially over a longer puller over this distance. If these pulleys were all at the same height, you'd have to have it tensioned very tight, and the belt may not actually touch these idlers. If they were at the same level, they could hang down. And again, if we're making a product with a 1 or a 5/1000 wall thickness and you're trying to barely touch it, if this belt's hanging at all, it's going to affect your process.
Especially if you have some portions of the belt itself that have some variation in them. And now what happens is as the belt comes around, it crushes the tube differently.
Correct. And wanted to show this. One of the manufacturers I've worked for over the years actually made twist pullers, and this shows a perfect picture of a puller where actually the lower boom is straight, but the upper boom is made to pivot. And these pullers initially were made for making straws, and you had the stripe on a McDonald's straw, and the stripe wanted to be twisted. So you actually could change the boom and actually cause a twist. I wanted to show this slide because we hope this doesn't occur in a lot of the tubing, but there are pullers made by other companies in the industry for doing this. But this is an example where we probably wouldn't want to be. We'd rather, and again, people mostly, instead of using something as drastic as this, would just be tensioning the belt to do this. But you can get units like this. So this one does show we want these belts parallel, not only in the length, but from front to back. So we just want to show that. And again, today we're making thinner wall tube, in some cases larger wall. You know, it could be a 300 or 400, 500,000 tube with a 5, 8, 10,000 wall.
Yeah.
It used to be Microbore was just tiny tubing, but in a lot of cases, the more difficult ones are actually the larger diameters now with the thinner walls. This contact pressure is really critical, Larry.
Especially in stiffer polymers, you know, a PET or a polycarbonate, PEEK, all could be problematic.
Yep. So again, we wanted to show, and again, you can see this is a 12-inch puller, and again, note that the idlers from this idler to this idler, they are a higher distance level than the end rollers are. So we do come up, we're only talking about probably 30,000s from here to here, but that distance up lets you not have to tension the belt. And this is where your tensioner is, not have to tension to this tight, but that little bit gives us an even pressure across these and doesn't let the belt possibly be sagging down. We want it consistent. So again, we're talking about the idlers. We've pretty much gone through this slide. And everybody, again, you will be able to obtain a copy, a link, so you can look at this at your leisure later on.
We're also using flat precision ground belts, not poly V, not timing belts. In previous experience with cutting very precision tubing and cutting lengths, we've gotten flat belts in the past, so I wanted to bring that technology to the micro unit. We wanted these to be extremely parallel to offer absolute precision. With that, we do.
And so basically what we're talking about here is using a flat belt. And the flat belt, think of a racetrack car with slicks. And as we mentioned in this, the flat belts have been used for years and years for high-speed processing of things like straws and things like cutting pens and swab sticks, or other parts where you needed very, very high cut-to-length accuracy in flywheel, Larry. I've used the flat belts for at least 30 years. And the flat belts tend to be thinner. You don't tend to get the set. So when you've got this flat belt, having very precise, first of all, we can grind them within 1,000ths, where poly V, about 5,000ths is the best on the thickness that you can do, and it's just not accurate enough. So the idlers and the end rollers are all flat, and the belts are very flexible and available in different materials.
Well, I don't know how many times I've actually seen product get rejected because there's black particulate. And when you actually do your due diligence and find out what happened, you're going to find out that the poly V belt is just spreading debris all over the place.
Correct. The flat belt, you do have the sheave up here is crowned, and you still have a tensioner. But it's far, far easier to do the tensioning, especially on a small 6-inch puller, and get extremely precise parallelism in both axes with a thin flat belt with even various materials. So we've talked about the type of belt, the placement of the rollers, the type of adjustment where we're using a linear bearing. So you can see how we are splitting hairs, but when we're trying to hold things to the tenths, this is what's necessary, which brings us to the next slide, Larry, where we're talking about the actual, okay, now we've got these belts perfectly parallel, but how do we come back in the importance of the actual gap between the belts and how much contact you're making on the tube itself? Every operator, they adjust a crank wheel, and I've seen from shift 1 to shift 2 to shift 3.
Absolutely, yes.
And
the gremlins of the night shift.
I mean, I used to call people adjusting the cut length crankers because they'd be cutting flywheel mode and they want the length a little bit longer. They'd actually crank this wheel tighter, a quarter of a turn, and all of a sudden the length got 10 thousandths longer. So by understanding that, by having the belt tighter against the tube versus lighter, so they tighten the belt, they're causing less slippage. By loosening the belt contact of the tube, there's more slippage. But I think everything we want you to understand today is that there is always a degree of slippage between the tube and the belt. So that's why we feel this gap is critical. So now, again, we've got everything very, very parallel. And pretty much standard method out there for medical tubing right now is using this. In this case, it's a pro scale. Where you have a linear scale, it's digital, it reads out, but you can come here and zero it, but it's better than nothing.
Well, there's no security on the zeroing of that type of device, and as well, like you said, anybody can re-zero it at whatever position that they want, so you're not going to get a true relative number.
So it'd be pretty difficult to validate.
Yeah, control. Well, if you can't truly measure it well, you can't control it.
Correct. So with that, this is showing the puller, in this case from a previous employer, and this was done probably 6-7 years ago. So this isn't anything new. This has been done where they actually put a servo to open and shut. In this case, it was done for taper tubing, where there were 2 different set points. So it went from one gap to another gap, and there was a simple roller up here with a laser, and basically it told you when you were in the distal versus the proximal. And it was a particular distance from the face, and it would open and shut this and give you a differential, 20 thousandths, 40 thousandths, whatever, but help not to crush it. So this isn't something new. It's been around. And what we're trying to do today is trying to make this more of a standard feature, because again.
Well, I mean, when it was done in the past, it wasn't, you can use servo systems to do it, but the mechanics of it didn't allow for any kind of precision.
Right. Not that was a very precise unit, but it wasn't designed for constant use.
Right.
Is because this is a relatively new feature. We're trying to make this more of a standardized feature because we feel this gap is critical. So hand wheels are gone. We've actually put 2 servos, and you can actually literally set what your level from the floor is. So you can set the bottom belt, and then you can go in here through password protection. And Larry, you were very specific that if we're going to be getting to the point someday where this is going to be a validation point, what this gap is for a particular product, you need to be able to validate, first of all, what 0 is. So we're going to have to provide some type of device, a load cell, whatever, that you would password protect, and somebody would come in and change a set of belts. They could go in and set what 0 is.
Well, yeah, it needs to be password protected. You don't want just anybody going in there and playing with the values.
And that's why once you have that, the 0 is, you could then go in and set, I want a 37 thousandths gap for a 40 thousandths product. but you could go back and you could set the actual gap for that product. And that's a starting point. So no longer, and especially it could be saved in recipes. So when you made product XYZ, you could program in, I want this gap, or I want to start up and I can start at a 10 thousandths gap and just move to that specific point. But now the potential to remove the operator variable is really there. And I think the thing that everybody's looking at is, could we use this for paper tubing? And it's something that has to be tested, obviously.
Yes.
With two servos, if they're designed properly, the potential is there. But you and I have talked about it for years, depending on the length of the transition, the distance between the length of your belt. There are so many variables. So you may not be able to, if you had a differential between the proximal and distal, you may have a differential actual of 100 thousandths, but we may only be able to have the belt differential go to maybe a 20 thousandths or a 30 thousandths. You may not be able to go the whole thing, but you could minimize some of this crush. But this is going to require some testing, which brings us to the next slide. One of the things we're talking about is really fully automating where we actually real-time interface with gauging. In this case, the gauge would have to be at a fixed distance attached to the puller, so that gauge point to the initial point of contact with the belt is a fixed distance. We'll call that the offset distance. Once we know that, you could actually say, I want a 5 thousandths differential, or crush differential, call it, so 5 thousandths between the actual tube size and the belt gap. And in this way, this puller gap is going to follow the product. So when you're stringing up, the belts will be all but closed. As the product would come up to size, it would maintain that gap and be extremely repeatable.
So that becomes more automatic, and that can actually be part of your recipe.
Absolutely. So it's something that this is something new, but it's not new. But here at Novatec, we're going to take that to the next level, and we're going to be working with that and developing that in our lab. And again, it's something that can we make this a validation point? Do you think it's possible, or should it be?
Well, you have the option of doing it if it's critical to the component.
Yep.
So anything that's critical to the component, you should be able to control. Previously, you wouldn't even be able to control it. So,
and with that, we're going to end today's session, and we then will be glad to be taking questions, and Larry and I will do our best to answer those questions for you. Thank you very much. Thank you very much.
Thanks, Bob and Larry. That was an informative presentation. I just want to remind anyone who hasn't asked questions at this point in time that to do so, there is a questions pane on the panel that's running down the right-hand side of your screen. You detach that, you type in your question, and I will ask them to Larry and Bob. But we do have a couple that have come in so far, gentlemen. So I will ask them, and between the two of you, you can decide which one answers. For gap validation, how precise should the processor list the actual recorded gap measurement?
Well, I would think that the precision of the measurement will come out through testing as the systems are built. There will be Novatec will end up putting a expected specification on that.
Our anticipation is that we will be able to programming it and be able to maintain within 1 to 2 thousandths is what our goal is. So as far as validation, you technically people want to leave a little bit of a range. They don't want to box themselves into a corner. So if you find yourself, at 10 thousandths, they might say plus or minus 2 thousandths, so 8 to 12 thousandths. So they will leave a bit of a range, whether it's the gap on a puller or even the hot gap distance.
All right, we have a question on the belt gap portion of your presentation. Should the belt gap be adjusted for different belt surface materials?
And I'll answer that. Absolutely. Every belt material, whether it's a 40 durometer natural rubber or 60 durometer or 70 durometer, or it's a different material, a urethane or a silicone or a sponge, they're all going to have a different degree of grip and thus the potential to slip. So for every belt, they should actually have to validate a different belt gap because there's going to be a different amount of traction or slippage with that type of a belt. So, yes.
Okay. Is there a general rule for belt contact surface length?
As always, your mileage will vary. You'd have to do some objective testing to see how it affects your process. At least now you will have the tools available to be able to adjust them very accurately and precisely to really determine that.
And as far as belt length traction, one of the old rules of thumb is if you saw that you were getting a lot of wear, what I call premature wear on your belt, it means that your tube is dramatically slipping the tube to the belt. So you're starting to wear, and it's a bad thing for medical because you're getting particulate. So if you're getting a lot of abnormal wear on your belt, you probably, the belt is asking, I need to be longer, I need more contact surface, because in many cases, people are just barely touching the belt to the tube because they don't want to crush the part. So if that helps the question.
Back to hot gap. Is there a general rule for hot gap with non-contact tooling when using a pre-skinner tooling package?
And I'll start and let Larry finish it. And typically, I've always liked to see a very short gap. When I see a longer gap, it tells me that the drawdown ratio may not be correct. So I think things are a lot more controllable with a short gap. Less room for the tube to be unsupported. We don't want to have to put air inside the tube, although we've done that in the past in some cases. But I would say short. Larry, is there anything you could add?
Well, I mean, if your tank gap is too far out, if you have a low viscosity, especially if you have a low viscosity material, and you're using internal air, it could be very difficult to control the air or control the size because it's out too far. The air has too much of an effect. So a lot of times you're better off being shorter. It all depends on your process.
Okay. Back to the matter of belt surface. If you're experiencing twist in parts, is non-uniform belt surface compression something that can cause this?
Well, belt tensioning and tracking can do it. Non-uniform tension, sometimes non-uniform tension is induced into the puller to make it twist.
Again, I've seen that where I've gone to somebody and they wanted a detwisting feature and they literally would tension the belt from the front to the back differently to try and tension the belt to get rid of the belts not being parallel front to rear. So it is very critical, and right now everybody's belt adjustment is a manual thing on these small pullers. There are larger pullers where it's done pneumatically, and this is another reason why we mentioned in the presentation that having the idler rollers down a lower surface than the two end rollers lets tensioning not be as much issue. It's a lot easier to get the belts flat, and that's another reason for using the flat belts over a poly V or a timing belt. The belts are a lot thinner, more flexible, so it is easier to get them to run true and to run flat because we don't want that twist.
Is there a recommended method of belt tensioning?
There actually are. The belt manufacturers, whether it's Habestat on the flat belts or other manufacturers, they do give specifications. You can get the machinist guide where there's a deflection unit over a distance and you check for deflection, but it will be different for every type of belt and every length or span of unsupported belt surface. So yes, and often it's a terrible thing, but people tighten until they hear the belt, the bearings creak, and then they back it off a little bit. It's very crude at best.
There are times where I've seen people adjust them with, torque wrenches, and that gives you some level of confidence, but it doesn't always work.
And again, that's why my preferred method is to look from the upstream end into the belt, into the width of the belt, front to back, and try to you tension them from either side so the belts are parallel in both directions, and obviously don't over tension. But there's still work to be done on the tensioning.
Okay. We keep going back between belt gap and hot gap, so let's take another hot gap question. When using contact vacuum calibration tooling, what is the typical hot gap spacing?
Typically is going to be 1/8 to 1/4 of an inch. Larry, would you?
Well, it depends on the application. I've had contact vacuum sizing applications where my tank has been out 12, 15 inches with an air ring before it actually hits the calibrator. I've had others where the front end of my tank was actually cut out to be a precision fit over top of the end of the die, so I can actually come in and just come right up and butt into it.
So it's going to depend on material, wall thickness, line speed, and obviously if the die is a good match, the pin and bushing, the proper drawdown. Because I've seen pipe people, they don't want to change the pin and bushing. They can make 2 different pipes from the same die, and you can tell when they're doing it. They're further away from the die is my first, when I see that.
As long as it does no harm, as long as your properties are good, and your production rates are where they need to be, and you're not generating a lot of scrap because of it.
And I think that's the big thing we're really pushing here is that this die gap can affect your material properties. You may make the same size tube with the same finish, but you can alter the property by having a bigger die gap. So it's just one of those variables, one more of those variables that we feel should be controlled.
Okay. I think we have run through our series of questions. So at this point, I would like to thank Bob and Larry for their informative talk. And I'd like to thank all of those who attended this afternoon for your attention and interest in this subject matter. As Bob indicated, we recorded this webinar, and soon you'll be receiving a link to that recorded version on our website, ptonline.com. You can listen to this webinar at any point in time, again, or you can forward the link to any of your colleagues who could not join us today. Once again, I'd like to thank all of those who joined us for this presentation. Thank you. Goodbye.